So part 2 of 13.6. We're going to talk a little bit more about the gradient. All right, so on Thursday, we went through kind of a long process of coming up with this idea of a directional derivative. So we wanted the rate of change of our function, of a multivariable function in any arbitrary direction. In the process of doing that, we came up with, let me just write this out I'm just going to do a quick recap. Our directional derivative. That was the point of what we did on Thursday, was to come up with this idea of a directional derivative. And our directional derivative is, if we have z equals f of xy, we want the rate of change of f in any arbitrary direction. So that's what we were after on Thursday. In the process of coming up with a way of calculating this directional derivative, we came up with this del operator. And you also hear del called nabla. And del we defined nabla. That's the name of the symbol is nabla. The nabla. And our del operator is defined, the 3 lines means defined, as ddx I plus ddy j, and if we had a third variable, we would have ddz k hat. So this operator, it has to operate on something to have some meaning. It has to operate on a function, and we'll end up in chapter 15, we'll use the del operator, use del, and we'll operate on other vectors to come up with some interesting things that we'll work with. Del doesn't have any meaning by itself. It's just these partial derivatives and our standard unit vectors. So it has to work on something in order for it to have any meaning. And we said we can use the del operator to find the directional derivative. So the directional derivative in the direction of u of f was del f dot u, where u is a unit vector. We want to do our dot product. We want to find our direction of our derivative. We want a unit vector to indicate our direction. And we used the del operator, this del f. We call del f the gradient function. So this del operator and the gradient function were 2 important things that came out of finding the directional derivative. So if we had, just to reiterate, z is f of xy, del f is df dxi plus df dy j. So we've operated on f with del. And you can also, we also said this, you will also see this sometimes written as grad f. And when you write it in text, they write in bold. I just put the little vector over it to remind us that this thing is actually a vector. So there's our directional derivative. This is our gradient function. And we said that one important property is del f gives the direction of the maximum rate of change. And we'll go through and talk about we'll talk about the proof of these ideas in just a second. So these were our big ideas from Thursday. The directional derivative. We came up with this del operator because in the process of finding a way to calculate the directional derivative, we came up with this quantity. So we treat this del as an operator, and we can write our directional derivative in a nice compact way like this. All right, so what I want to do before we go through, and we talk quickly about the proofs of the properties of the gradient. We talked about some properties on Thursday, and we'll prove those properties are very easy to prove. I have a little demonstration that shows us an idea of the directional derivative. So here is our picture. All right, so what we have here is, here's my surface. So I have my surface. This little circle I can change my unit vector. So this is the direction that I want my directional derivative in. And, oops, I turned that upside down. And this, I can move my point around on the surface. So there's the point on the surface. And this gives us our level curves. And it shows the unit vector in red and the gradient in blue. So there's our surface, and the gradient is pointing in the direction of the maximum rate of change in our function. So it's kind of pointing straight uphill there. And if I move my unit vector around relative to my gradient, if I move my point around, I get a different gradient. So over here on this point in the surface, the maximum rate of change is up the hill there. So that's what our gradient is telling us about the direction of the maximum rate of change on our surface. And this gives us our particular unit vector, and if our gradient and our unit vector are pointed in the same direction, then our unit vector is pointed in the direction of the maximum rate of change.
Mr. Weaver?
Yes?
Would the gradient be zero if you were exactly on the continent?
That's about as close as I can get it. So right there on the top of the hill, del f is 0, negative 0.04, so the gradient would be 0. Because right at the top, it's right around that point at the top of the surface. It's essentially flat, right? So there's no rate of change there. And we will use that idea that the gradient is 0 at a maximum or a minimum to maximize or minimize multivariable functions. And we'll also, Max asked the other day on Thursday, said when we talked about single variable functions, we talked about the rate of change and the derivative had to do with the slope of the tangent line. We found the slope of the secant line and kind of took the limit as delta x approached 0, and we're finding the slope of that tangent line. He said, well, why aren't we talking about tangent planes since we're talking about multivariable functions? Slope and tangent planes seem like they're related. They are related, but we need one thing still before we can define a tangent plane on our surface. What two things do we need to write the equation of a plane? We need a point on the plane and what gave us our direction numbers when we wrote the equation of a plane? A special kind of vector?
Tangent?
Not a tangent vector, but a normal vector. We needed a normal vector. So we need to know how to find a normal vector in order to define our plane, our tangent plane at a point. And the gradient's going to help us with that as well. And we'll talk about that on block day. So this is the idea of our directional derivative, our gradient at a particular point. The gradient points in the direction of the maximum rate of change anywhere we are on this surface. So if we look here, just one more example. Here I am on the surface on the side there. Whoops, I turned it upside down. And the gradient is pointing at the steepest route up that hill. That's my gradient pointing right up there. All right, so let's go back to our gradients and talk about our properties. A couple of the properties that we talked about. We said if del f equals 0, if our gradient equals 0, then that was our first property, then any directional derivative was 0. And this should be a 0 vector. If our gradient is 0, then our directional derivative for all unit vectors, for any direction. So if our gradient is 0, our directional derivative is 0. That's kind of what we just talked about right at the top of that surface. Our directional derivative is 0. So it doesn't matter which direction we go, our directional derivative is 0 because we're kind of, it's essentially flat up on top there. Well, our directional derivative is del f dot u. And if our gradient is 0, we have 0I plus 0j dot u, and that's got to be 0. No matter what u is, this is going to be 0. So our directional derivative is going to be 0 if our gradient is 0. So that was one property. The second property, we said the direction of the maximum increase is in the direction of the gradient. We said that's given by del f. And the magnitude of this maximum increase is the magnitude of del f. Well, we can write our directional derivative for this property. We can write our directional derivative is del f dot u. And if we let the angle between the gradient and our unit vector be phi. So that's our angle. We can write our directional derivative del f dot u. An alternate way to write that is the magnitude of del f times the magnitude of u times the cosine of phi. And the magnitude of u is a unit vector. So this is going to be a magnitude, this is going to be a maximum, so del f dot u, since u is a unit vector, is going to be the magnitude of del f times the cosine of the angle between them. It's going to be a maximum when the cosine of phi equals 1. Because the cosine varies between positive and negative 1. So this quantity is going to be a maximum when cosine phi equals 1. So that tells us that phi equals 0, and del f and u are in the same direction. So our direction of maximum increase is in the direction of del F. So when our gradient is in the direction that we want to go, that's going to be our maximum increase. And the magnitude of that maximum increase, because cosine phi is 1, the magnitude is going to be the magnitude of del F. And we said our third property is related to this second property. We said the direction of the minimum increase or the maximum decrease is the opposite direction of del F. Well, that happens when cosine phi is -1, or phi is 180. So del F and our unit vector are in opposite directions. So the direction of the minimum increase or the maximum decrease is in the opposite direction of del F. So these two are kind of combined into one. It's minimized when cosine phi is -1, but I still get the same magnitude. So those two are related. So the gradient gives us the direction of the maximum increase in F. The opposite direction of the gradient is the direction of the minimum increase in F. We can think of the minimum increase as the maximum decrease. Steepest route downhill. All right, there's another important property that's going to be actually kind of more important than the directional derivative that I want to talk about next. So questions on what we talked about here. So the big takeaways here. Gradient helps us find our directional derivative. The maximum directional derivative is in the direction of the gradient. The magnitude of that maximum directional derivative is the magnitude of the gradient. All right, next property. I'm just going to call it another property. And this one turns out to be probably more important than the other one. All right, so what I want to do is draw a portion of a level curve of F. So here we are in the plane. And here's, I'll draw it in red. This is a portion of a level curve. And on a level curve, and I'm going to say z equals f of xy. On a level curve, what do we know about my function? How did we define a level curve? A function equals what? Constant. So z equals a constant. I'm going to make u, the direction that I want to find my directional derivative, a unit tangent vector. So I'm going to say this is a unit tangent vector at this particular point on this level curve. So u is our unit tangent vector on the level curve. So our directional derivative, z is a constant in the direction of u, has to be what? 0. F is not changing on the level curve because z is constant. So I'm going to write my directional derivative is 0. So del f dot u equals 0. What does this tell me about del f and u? If the dot product is 0. They are, what was it? Perpendicular? and for vectors we call them orthogonal. So del F, and still 2 dimensions. We usually use orthogonal for vectors and surfaces. So del F is orthogonal to U. And U was any arbitrary unit tangent vector on the level curve. So del F is going to be orthogonal to any level curve. So or we call it normal. We usually call it normal. So del F is normal to any level curve. So our gradient vector is normal to level curves. So that's going to be a very important property of the gradient. Gradients are normal to level curves. Well, if we think of, and it makes sense because if we think of our level curves, if we think of a topographical map, the direction that we're going to go steepest up the hill is perpendicular to those curves that represent the altitude on our mountainside. And we'll use this idea when we have a function of 3 variables, when we're talking about a surface, to come up with our normal vector to our surface. So del F is normal to any level curve. The maximum rate of change of F is normal to the level curves. And we can turn that around and say, if we know the direction, if we know our gradient del F is normal to level curves, the direction of the minimum, or of 0 increase, 0 change in F, is tangent to the level curves. We can calculate del F, and what was our quick shortcut for finding a normal vector to a vector in the plane? So we said del F points in direction of maximum increase. It's perpendicular, or sort of normal to the level curve. And we said that the directional derivative in the direction of a tangent vector to the level curve is 0. There's no change. So if del F is xi plus yj, that's pointing in the direction of the maximum increase, normal to the level curve. What is a vector that points in the direction of 0 increase, if we know our gradient vector? Well, how does it need to be related to our gradient? Our gradient is normal to the level curves. It's normal to that unit tangent vector to the level curve. So how does it need to be related to that vector? If it's going to point in the direction of the tangent vector to the level curve, the gradient makes what angle with the tangent vector? 90 degrees, right? So we need a vector that is perpendicular, that's normal to del F. Well, if del F in the plane is xi plus yj, how do we quickly and easily find a vector that is normal to that vector? Switch the x's and y's, change the sign on 1. So once we find the gradient at a particular point, We know the direction of maximum increase, and we can also quickly and easily find the direction of no increase, perpendicular to the gradient. That gives us a vector in the direction of the tangent vector to the normal curve. And we do that by switching the x's and y's, changing the sign on one. So we'd be getting a vector pointed this direction or a vector pointed back that direction. Either of those would point in the direction of no increase on our surface. So the gradient at a particular point gives us a direction of maximum increase, and in the plane we can quickly and easily find the direction of no increase. All right, questions here? So this property of the gradient, that it is normal to level curves, very important idea. We'll use that a lot. All right, let's do a quick example, and then I think we get to do this today. Yes, we get to do one of my favorite examples in this that has to do with the gradient. So let's let f of xy equal xy. We want to find a normal vector to the level curve f of xy equals -3 at 1, -3. Or sorry, -1, 3. So our surface, what kind of surface is f of x equals xy? We get z equals xy, or x equals y over z, y equals x over z. Sorry, z over y, or x over z over x. Those are hyperbolas. So we end up with a hyperbolic parabola. All right, so we want a normal vector to our level curve. F of xy equals -3. So xy equals -3. And we know this normal vector to a level curve, that's asking us really in code to find the gradient. Del f is normal to level curves. So it's asking us to find the gradient. So del f, what is the gradient of this function? The f dx in the I direction. So what's the derivative of this with respect to x? Y. So we get yi. Derivative with respect to y in the j direction, j hat direction. So we get x j. There's del f. And it says at -1, 3. Our gradient is 3i minus j. So that vector would be normal to the level curve f of xy equals -3 at that particular point. Normal to level curve, code name gradient. All right, let's go through this is my favorite kind of problem that has to do with gradients. My favorite kind of problem that we do. Questions on this example? All right. So we have this temperature gradient, this temperature function. T of xy is 100 minus x squared minus 2y squared. This gives the temperature at any point on a metal plate.
Temperature in Celsius or Fahrenheit?
Doesn't matter.
Or Kelvin?
Either whatever we like.
Definitely Kelvin.
So this is our temperature field. First off, what kind of field? What are our level curves going to look like on this field? Ellipses. So our temperature field gives us elliptical level curves. All right, we want to find the path of a heat-seeking particle that starts at the point 43. All right, so this field, this function gives us the temperature on a metal plate. We want to find the path of a heat-seeking particle that starts off at point 43. Yeah, heat-seeking particle. Yeah, that's the part that I really like. Well, what's a heat-seeking particle? All right, so the heat-seeking particle is going to move in the direction. What direction? How are we going to figure this out? What direction is the heat-seeking particle going to move in? Towards the, not necessarily the center, but towards the maximum temperature, right? The maximum increase in temperature. So at any point, it's going to say, I want to go in the direction where the temperature is increasing the fastest. I want to get to the highest temperature. So what points in the direction of the maximum increase in temperature? The gradient points in the direction. Del T. So that's going to point in the direction of maximum temperature increase. So the particle is going to say, oh, it's warmer in that direction, I want to go in that direction. At each particular point in this temperature field. That changes as it moves. So del T here, our gradient of our temperature field. Del T is dt dxi, so I get minus 2xi, plus dt dyj, so I get minus 4yj. So there's one piece. There's one piece. This is going to point in the direction of the maximum temperature increase. Well, let's say that our particle is traveling on the path, some random path, r of t. And we're going to say this is some function x of t I plus y of tj. So there's the path of our particle. What is another vector that is also going to point in the direction of, that's going to point in the direction that this heat-seeking particle is moving? If our position vector is r of t, what vector points in the direction that our particle is moving as it moves through space? Anybody have an idea? No ideas? How about r prime? Isn't r prime tangent to our path? Doesn't r prime point in the direction of motion? R prime points in the direction of motion. R prime is going to be x prime of t I plus y prime of tj. And that points in the direction of motion. So we have del t pointing in the direction of motion. It's going in the direction of maximum maximum temperature increase, and we have r prime pointing in the direction of motion. So we can say r prime, they're pointing in the same direction. R prime is going to be some scalar multiple of del t. They're pointing in the same direction, so one is a scalar multiple of the other. This equation is going to let us find our path. So we can say minus 2xi minus 4yj equals, and I'm going to put my scalar multiple on the other side of the equation. So I'm going to say equals c times dx dt I plus c times dy dt j. The gradient is a scalar multiple of r prime. And I'm going to equate these two components. So c dx dt equals minus 2x, and c dy dt equals minus 4y. I'm going to isolate dt here. So I get c dx over negative 2x equals dt, and dt also equals c dy over negative 4y, and now I'm almost home free. Both of these equal dt, so I get I get 2 dx over x equals dy over y. Just multiplied both sides by negative 4. And how do I solve this? I have all the x's on one side, all the y's and the derivatives on the other side. So I have a separable differential equation. I can integrate both sides. So I integrate both sides, and I get 2 natural log x equals natural log y plus a constant of integration. I'm going to call that C1. And now what can I do with this equation? How do I get x? I don't want the natural logs in there. How do I get x as a y? Take it to the e. I need to do one thing here first. Natural log of x squared equals natural log y plus c1. Now I exponentiate both sides. So I get x squared. Exponentiate both sides. Exponentiate both sides. I get x squared equals, and I get a c2 y. When I exponentiate this side, I get y plus e to the c. Actually, I get e to the y plus c1 on that side, and that's e to the y, e to the c1. And e to the c1 is where I get my c2. What's that? So when I'm just saying for this side when I raise this to the e power, I get e to the y. Natural log y. Natural log y plus c1. I forgot my natural log. Right. There we go. Forgot to write my natural log. So that's where that C2y comes from. That's e to the C1. And I need to find my C2. We know that the particle starts at 0.43. So that lets me solve for my C2. So 16 equals C2 times 3, and C2 is 16/3. So my path is y equals 3/16 x squared. So that is the path on that plate that the particle is going to follow. And if I sketch out my level curves here, we said we get ellipses. So those would be my level curves, and my particle is going to travel on a little parabolic path. I love these problems. Because we have the gradient, we have vector valued functions with r prime, r and r prime, we have a separable differential equation. All these things combined into one nice problem. So questions on what we did there. So the big picture here, our gradient pointed in the direction of maximum temperature increase, the direction of motion, and r prime pointed in the direction of motion as well. So we can equate those two. They're scalar multiples of each other. All right. So that was a little bit more with the gradient. Gradient, important takeaway today, gradient is normal to level curves. And we will use that on Thursday when we talk about surfaces in 3 dimensions. Our gradient turns out to be normal to our surface at a particular point. And then we can get to our idea of the tangent point. All right, homework. There we go.